Now we are going to second statement of thermodynamics, Kelvin Planck statement. Okay. So eta equals W by Q net Q1 1 minus Q2 by Q1. W can be written as a Q2 by Q1, or W equals Q2 minus Q1 minus Q2. So that way I can get Q2 by Q1. So W net less than Q1. If Q2 equals 0, if Q2, that is W net equals Q1, that means eta equals 1. So mean heat energy will produce work violating Kelvin's Planck law. Okay, so there must be some heat transferred to sink. If there is no heat transfer to sink, that means it is violating Kelvin Planck's statement. Okay, perpetual motion machine of second kind. Perpetual motion machine of the second kind, a PMM2. Okay, so perpetual motion machine of second kind, a PMM2, is impossible, is coming from second law. If the engine exchanges heat only a single thermal reservoir, like only source is there is no sink, so in which heat is supplied completely converted into equivalent amount of energy. Okay, source, system, sink. Okay, and you are getting work. So perpetual motion machine second kind, it says like there is no sink, only source is there, work output is there. So this is impossible. Okay, this kind of machine is known as PMM2. Clausius statement: heat always flows from a body at a higher temperature to a body at lower temperature. The reverse process never occurs in system. So Clausius statement: heat flows from higher temperature to low temperature body, and reverse cannot occur. The reverse flow cannot occur. Refrigeration and heat pump. So first again you draw one refrigeration cycle. Again details I will discuss later when I will be teaching refrigeration part. Okay, so there will be one compression system, then there will be one evaporator system, okay. So this is compressor we are giving, expander, work coming out, atmosphere, and heat is going to atmosphere, Q1, evaporator, this is taking T, Q2, this is 1, this is 2, this is 3, this is 4, this is condenser. Okay, and our cycle is happening like this: atmosphere, I have one cycle, then I have body A at T2. T2, so Q1 is flowing here, Q2 is flowing here, and WE is going out, WC is going in, and whole cycle is going on. Okay, if I can represent like E, work is going out, the C, work is in, and atmosphere, work, heat is going out, and from evaporator heat is getting entered into the system. It is just opposite of your steam cycle. In the steam cycle, actually there was one condenser, heat was going out, there was a turbine, there was a boiler system. So this is just reverse of your steam engine cycle. So coefficient of performance of performance COP. So COP is defined as COP equals desired effect and work input equals Q2 divided by W equals Q2 divided by Q1 minus Q2. So COP of heat pump equals Q1 by Q1 minus Q2. Okay, so COP, this is COP of a refrigeration system, REF. So COP refrigerant equals COP of HP, or I can write COP HP. Okay, so COP HP will be like, relation is like this, HP minus 1. Yeah, reversibility and irreversibility Carnot cycle. So from second law, all process comes under reversible ideal process and irreversible natural process. Okay, Carnot cycle. So Carnot cycle is a reversible cycle. Okay, a reversible cycle is an ideal hypothetical cycle in which all the processes constituting the cycle are reversible. So first you draw one again piston cylinder arrangement. Okay, here one okay, so this is diathermic cover, adiabatic wall. So adiabatic means like no heat transfer will be allowed, even mass transfer not allowed anyway. So no heat transfer also allowed, or energy transfer is allowed. And this is piston work WP out, and diathermic wall allows heat transfer. Diathermic cover means allows heat transfer, HT means heat transfer, but not matter. Okay, and this is adiabatic cover. Okay, and source Q1 is going there, and sink T2 Q2. Okay, Q2. So Carnot engine stationary system. So cycle is an ideal hypothetical cycle in which all the processes constituting the cycle are reversible. So this is called reversible cycle, okay, or Carnot cycle. So it is having 4 processes. Carnot cycle, it will have a reversible isothermal process, reversible isothermal where from first law it will be U1 equals U2 minus U1 plus W1 to 2. This is called from first law. From ideal gas law, from the cylinder cover is in contact with the diathermic cover A. So, B reversible adiabatic. Reversible adiabatic process. So, A replaced by adiabatic wall B. Okay, adiabatic wall. This is B. This is A. Okay, and WE work done by the system adiabatically. So, the first law says 0 equals U3 minus U2 plus W23. So, this is the formula W223. Okay. A reversible isothermal process. Reversible isothermal process, again from first law, it is coming like Q2 equals U4 minus U3 W34. Okay. Reversible, this is D, reversible adiabatic process. 0 equals U1 minus U4 minus W41. So, we are getting two reversible isothermal and two reversible adiabatic. Okay, if I want to plot here, it will be like this P V. Okay, so 1, 2, 3, 4 process like this. Okay, WP, WE, Q1 and Q2. So 1, 2, 4, 2, 2, 3, 1, 2, 4, 1, 4 and 2, 3, 2, 3. I can write 4, 1. This is reversible adiabatic. And 1 to 2 and 3 to 4 reversible isothermal process. Reversible isothermal process. So, Q1 minus Q2 equals W1 to 2 plus W2 to 3 minus W3 to 4 plus W4 to 1, or summation of Q net cycle equals summation of cycle W net. Okay, a cyclic heat engine operating on the Carnot cycle is called Carnot heat engine. Okay, cyclic heat engine operating on Carnot cycle is called Carnot heat engine. Again, though the heat engine, so T1 here it is coming compression system. So pump or compressor power is giving, and from here turbine T WT is coming. This is T1, this is T2 will be coming here, T2, and cycle will be like this. So continuously flow will be going on. So pump D, turbine B, this is source is here. So from here Q1 is coming, and T2 sink. Okay, Q2 going, temperature T2 sink temperature, and this is 4, this is 1, this is 2, this is 3, and fluid is flowing like this. So W net is equal to W net equals WT minus WP equals Q1 minus Q2. Okay, so this is Carnot heat engine, a steady flow system. So reverse heat engine, if I want to draw, first again you draw heat exchanger. The later stage I will discuss details about heat exchanger. Heat exchanger means it will be releasing heat from the system, okay, or it will be getting heat. So this is T1 and Q1, again turbine is here, okay. So W turbine going out and fluid is flowing like this, and T2 is here, okay, and okay, this cycle again, the same similar cycle I am drawing here. So pump, when you are talking about refrigeration, or when you are talking about heat engine, like say thermal power plant, so just case will be just opposite, okay. Q2, T2, from T2 you are taking heat and you are supplying the system, but in other case it was just opposite, okay. So the reversed heat engine, this is called reversed heat engine, okay, or it's called refrigeration cycle. So efficiency of the reversible heat engine is that efficiency of the reversible heat engine, eta reversible equal eta maximum possible. Carnot engine will be giving maximum efficiency. No engine can have more efficiency than Carnot efficiency, okay. 1 minus Q2 by Q1 reversible, okay. If it is irreversible, then there will be much more losses. 1 minus T2 by T1, so eta reversible T1 minus T2 divided by T1. So this is the formula, okay. So Carnot engine will have the highest efficiency. You cannot get more efficiency than Carnot cycle. Other system, practical system, will have lesser because there will be several other losses. Carnot cycle assumes everything is reversible. So entropy concept is coming from the second law. So thermodynamics, in the thermodynamics is the study of 3 E's: energy, equilibrium, and entropy. First law says law of internal energy. First law says law of internal energy, okay. Second law is the entropy, concept of entropy it will give, because it will say losses. So when losses are there, entropy will be increasing, okay. So property of entropy, let us say PV, again PV, and two processes are there: initial stage, final stage, R1 reversible, and going back to I again, R2. So two reversible path R1, R2 between two equilibrium states I and F. From Clausius theorem says R1 reversible process, dq t equals 0. Okay, this can be replaced by integrating R1 I to F dq by T plus dq by T R2 F to I, because cyclic process, equals 0, or I can write integration of dq by T I to F R equals minus dq by T R1 R2 I to F. Since R2 is reversible, I to F, this should be F to I. Okay, since R2 is reversible, R1 I to F dq by T equals R2 I F dq by T. This property is called entropy. So, SF minus SI equals I to F dq by T, or ds equals dq reversible by T, when two equilibrium states are infinitesimally near. So, ds is exact differential because S is a point function and a property, exact and a point function, exact because exact differential because S is a point function and a property. Subscript R in dq indicates that heat dq is transferred reversibly. Okay, so this subscript R implies heat transferred reversibly. For heat dq transfer reversibly. Okay. The word entropy actually is coming from tropy, is transformation. By Clausius theorem, this entropy term came up. Okay, it is extensive property. So, entropy is an extensive property. Is extensive property. And unit will be J per K, or small s if I write, then S by meter, then it will be J K K. Okay, if we write small s, then normally we divide by kg. Now we will solve two problems. Problem 6, the cyclic heat engine operates between a source temperature of 800 and sink temperature 30 degree. The least rate of heat rejection per kilowatt net output of the engine is, so we have to find it. So, eta max, so first you draw the figure, heat engine, T1 equals 1073, this is source. Okay, and W equals Q1 minus Q2 1 kilowatt, and Q2 sink T2 equals 303 K Kelvin. Okay. Now eta max equals eta reversible process equals 1 minus T2 by T1. So 1 minus 30 plus 273 800 plus 273 equals 0.718. So 71% efficiency, 72%. Now net work output, input heat equals eta max. Q1 equals 1 by 0.718 equals 1.392 kilowatt. So it is coming Q2 equals Q1 minus W net equals 1.332 1.392 92 minus 1 equals 0.392 kilowatt. So this is least rate of heat rejection. Another problem, a solar collector absorbs 1880 kilojoule per meter square energy when plate operates 90 degrees centigrade and transfer energy as a heat to the fluid within heat engine. The engine rejects heat to atmosphere. The minimum collector area required to produce 1 kilowatt of useful shaft power is dash meter square. Assume atmospheric temperature 20 degree. So efficiency of the reversible heat engine. The maximum efficiency for the heat engine between the collector plate temperature and the atmospheric temperature is eta max equals 1 minus T2 by T1 equals 1 minus 293 by 363 equals 192, where T1 actually 273 plus 90 equals 363 K, T2 equals 273 plus 20 equals 293 K. The efficiency of any actual heat engine operating between these temperature would be this then efficiency. So Q min W eta max equals 1 kJ per second, 0.192 equals 0.521 kJ per second. So minimum area equals 1880 0 equals 10 meters square. So if plate is circular, So d pi by 4 d square equals 10. So from there you can calculate d. Okay. So I am not calculating this one. I left for you. Thank you very much for this lecture. Next day or next week, I'll start the topic heat transfer. Thank you very much.